This is the first lecture from Chapter 10. It's an in-depth look about chemical bonding, and although we've gotten a real brief introduction of bonding as far as definitions of covalent versus ionic, this looks at bonding more from an energetics point of view, which is the driving force for making a chemical bond. And the first thing I want you to realize is that a chemical bond is not a physical entity. It is actually an electrostatic attraction. If it's an ionic bond, the attraction is between the positive charge of a cation and the negative charge of an anion. If it's a covalent bond, the bond is actually also an electrostatic attraction, but the attraction is between the negatively charged electrons of one atom and the positively charged protons on another one. Okay, so bonds, again, even though we draw these lines, there's no physical entity there. It's really just an attraction holding them together. There are a couple of key bonding theories which we will ultimately go over. One is called the valence bond theory, and the other one is called the molecular orbital bonding theory. Okay, and why do scientists feel like they need bonding theories? You can predict which atoms will bond with each other and what type of properties they'll have. Can also be used to predict the shapes of molecules, which we will go over in more depth in this chapter. So let's take a look at the energetics of a chemical bond forming. So we have energy here on the y-axis, and imagine that there are two atoms that are thinking about bonding, okay? And when they're a certain distance away from each other, when they're not bonding yet, so they're separate, completely separate atoms, we call that energy level 0, okay, when there's no chemical bond at all starting to form. Now, as the two atoms that are bonding start to approach one another, as they get closer to each other, the energy starts to decrease. Remember, energy decreasing is a good thing, okay? Low energy things are more stable. So our world likes low energy. So there's a point at which the energy of these two atoms approaching each other gets the lowest possible that it can. And it's at that point that a bond is formed. So at that point we call it a chemical bond. And so what information can we get from this? We can get the bond energy, and we can also get, I'm going to move this up here, there. Okay, we can also get the distance between the two atoms when they're bonded to each other. So internuclear means between nuclei. We can get that distance. Here, it looks like a happy face. All right, so what do you need to be able to do with this graph? You need to be able to interpret this type of graph, okay? We have talked a bit about ionic and covalent bonds, so don't forget the basic definition. Ionic bond is when an electron has been transferred from one atom to another to make charged ions, and then the covalent bond is when electrons are shared between two atoms. There's a third type of bond we haven't talked about much, but you need to be aware of. It's called a metallic bond. This is not really technically a chemical bond. I'll show on the next slide what a metallic bond looks like, but I just want you to be aware of it at this point. So let's look at diagrams of all of them. An ionic bond is made up of ions, cations, and anions that are held very close together by a strong electrostatic attraction. Covalent bond, again, they're sharing electrons. What holds them together again is an electrostatic attraction, but again, it's from the electrons of one atom to the protons of another atom. Here is metallic bonding that we really haven't talked about much. So you have a bunch of metal. Let's just say you have a bunch of neutral sodium. What happens when you have metal atoms together, any metal, okay, so it could be aluminum foil, or a piece of tin. The valence electron on metals are quite loosely held. So let's look at sodium. Sodium has one valence electron. It's in group 1A. Valence electrons are loosely held. So what happens is all of the valence electrons in the metal are kind of shared by all of them. And so you can almost think of a metallic bond as losing the valence electrons, so what's left are almost cations, not pure cations. But so these would all be, let's see, to show metallic bonding, you would think of a bunch of sodium cations, all of them having given up their valence electron, surrounded by a sea of electrons. So kind of all of the valence electrons of the metal kind of float loosely to the top and are shared by all of the cations. So we call that metallic bonding a sea of electrons shared by all of the metal ions. That's just a definition you would need to know. So we're going to look at ionic bonding in a little bit more depth, and we're going to learn, you may have heard about Lewis structures, so we're going to learn about those next for ionic bonding and covalent bonding. The first thing to be aware of, a couple facts if you're not already aware, is that metals become cations. This is supposed to be form. Metals form cations. Okay, metals have low ionization energies, which means they give up their valence electrons easily, and therefore they become cations. Nonmetals tend to form anions. Nonmetals have a relatively high electronegativity, and they also have a high ionization energy. What does that mean? Well, that means they're reluctant to give up their valence electrons, therefore they have a high ionization energy, and they have an attraction for extra electrons. So that's why they're more likely to form anions. So it's kind of a match made in heaven. A metal and a nonmetal make ionic compounds. So let's look at, on a molecular level, a covalent bond. So covalent bond, you have two nonmetals. So let's look, for example, like two fluorine atoms that are going to bond. So each of these fluorine atoms have 7 valence electrons. It's in group 7A, right? And neither one of these wants to give up a valence electron. No nonmetals do in general. They both have a high electronegativity. In fact, fluorine has the highest electronegativity of all elements. And so the best way they can lower their energy is to share their valence electrons. Okay? So what happens, you can think of it then, I'm going to put X for the shared electrons. So by sharing electrons, neither one wants to give it away, by sharing electrons, they each end up with a full octet. All right, so that's two nonmetals making a covalent bond. What is the electrostatic attraction in metallic bonding? That's just pure metal. And it's the attraction between essentially the cations when the metal has given up its valence electrons to all of the negatively charged electrons that are shared with all the metal cations. So that's kind of what holds them together. Another very important key point, conceptual understanding here. All bonding involves valence electrons. Okay? All chemical bonds involve the valence electrons. What is a valence electron? It is the electrons in the highest energy level. Okay? So it really is only the valence electrons that are involved in chemical bonding. So it's important to be able to tell how many valence electrons an element has. As a reminder, we've mentioned this before, but as a reminder, the valence electrons for an element is equal to the group number that that element is located in. So this first group is 1A, and they all have 1 valence electrons. 2A have 2 valence electrons, 3A, 4A, 5A, 6A, 7A, and 8A. Of course, helium's an exception. Helium is in group 8A, but it only has 2 valence electrons just because it's a little strange. I'm going to go over rules now for drawing Lewis structures. Lewis structures are also known as electron dot structures. You have probably seen Lewis dot structures. It looks something like this, where it's a chemical symbol and it has a certain number of dots around it. That is a Lewis structure. These dots represent valence electrons, and it's just a shorthand way that chemists use to predict what type of bonding is going to occur. So let's look at the Lewis dot structures for atoms on their own first. So for example, oxygen is in group 6A, which means it has 6 valence electrons. So if I asked you to draw the Lewis dot structure for oxygen, you would have to place those 6 electrons around the chemical symbol for oxygen, which is O. So the rule for that is think of an element as having 4 sides and put a valence electron on each of the 4 sides, and do not pair any valence electrons until each of the 4 sides has 1 dot. So I've used up 4 dots so far, but oxygen has 6 valence electrons, so I need to add 2 more. So now you can start pairing. So here's the correct Lewis dot structure for oxygen. It doesn't matter which of the 4 sides have the paired groups on, so these 2 structures are equivalent. Just a little hint about Lewis dot structures for elements. All elements like to have 8 valence electrons. You can see by looking at oxygen that it would like 2 more electrons to give it an octet and to have all the valence electrons paired. And because of that, oxygen tends to make 2 bonds. Okay, so however many electrons they need to get an octet is how many bonds that element wants to make or tends to make. I like this diagram just because it's visual. It shows you the Lewis dot structure for all of the elements. Of course, all of the elements in group 1A have 1 valence, so they all look quite similar. Group elements in 2A have 2 valence electrons. So let's look at carbon. How many bonds does carbon usually make? You might know that it makes 4, but you may not. That's fine. And that's because carbon has 4 valence electrons and needs 4 more valence electrons to get an octet. And so it tends to make 1, 2, 3, 4 bonds. Nitrogen needs 3 more electrons to get an octet. So nitrogen tends to make 3 bonds. Carbon makes 4, nitrogen makes 3, oxygen tends to make 2 bonds, and fluorine tends to make 1 bond. The noble gases do not bond in general because they already have a full outer shell that is 8 electrons around them. All right, so be able to draw the Lewis structure for any element I give you. I'm going to switch to drawing Bohr models for a minute because the Bohr models are convenient to show chemical bonding. So here's the Bohr model for a sodium atom and a fluorine atom. Sodium has 11 electrons. Fluorine has 9 electrons. And so if you were to draw an electron configuration for sodium, it would look like this: 1s2, 2s2, 2p6, 3s1, 2, 4, 10, 11, yeah. And so if you were drawing a Bohr model for sodium, you'd have to say how many subatomic particles in the nucleus. Then the first energy level has 2 electrons. First energy level has 2 electrons. 1, 2. The second energy level has 2 plus 6, or 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And in sodium, the third energy level has 1 electron. And here it is. Here's the valence electron. So in order to get a full outer shell, sodium can very easily lose its 1 valence electrons, and when it does so, this whole outer shell goes away, and what becomes the outer shell for the sodium cation is energy level 2. All right, fluorine it's in group 7A, so it has 7 valence electrons. Okay, so fluorine, in order to get 8 valence electrons, gains 1 electron. So sodium and fluorine, a match made in heaven. Here's what the Born models look like after sodium has given away an electron and fluorine has accepted an electron. The original n equals 3 energy level has no electrons on it because the 1 electron that it did have on it was given to fluorine. Therefore, this is the sodium cation. Fluorine, which had a hole in its second energy level, now has a complete energy level because of the electron donated by sodium. And so what makes this a bond once they transfer that electron is a strong electrostatic attraction between the cation and the anion. If we were to show an ionic bond forming using Lewis structures, this is how we would do this. And I can guarantee you there will be a question like this on your next exam to be able to demonstrate this, so you might want to jot it down. So you start with the neutral atoms showing the Lewis structures of each. Of course, sodium has 1 valence electron, chlorine has 7. Typically we use arrows to show the transfer of an electron. And then what would be formed? Once sodium gives away an electron, it has a positive charge and it's naked. Okay? So cations are always naked. They're shown with no electrons around them. Because oh boy, here we go. So the anion and the chlorine has accepted that electron, so it now has a negative charge. So make sure that you can show this type of Lewis structure ionic bond forming. Now here we go into the energetics of ionic bonding. This is pretty complicated, so you may have to go over it a couple times. There are several steps as far as breaking it down into energy transfers in making an ionic bond. For example, one of the steps is ionization energy for the metal. Remember that metals give up electrons and that costs some energy. So in the case of sodium, it takes 495 kilojoules per mole to remove that valence electron of sodium. Here they go again. My doggies are wound up. All right, so that costs energy. That is endothermic. Okay, so that costs energy. That's a price to pay. Then we get some of that energy back because when chlorine accepts an electron, it releases energy. Okay, releases. All right, so the scientists figure there's got to be a missing puzzle piece because what do we have in net energy from these two steps? If you add them together, we end up with a positive 146 kilojoules per mole. With that positive sign means that these two steps together are endothermic. Okay, that is an energy cost. That means we've got to put in that much energy. However, we know that if we mix the element sodium together with the element chlorine, the energy is actually released. Okay, the very energetically favorable process. So we know a puzzle piece is missing because this is telling us it's going to cost energy, and in fact, it doesn't. It releases energy. So there's a piece missing. And that missing piece is the electrostatic attraction, which is very energetically favorable, between the anions and the cations. That electrostatic attraction is called lattice energy, and it's very exothermic. So again, lattice energy, which is that missing puzzle piece, always exothermic. That means energetically favorable. It means it releases energy when it happens. And lattice energy is a very difficult property to measure, and so scientists tend to calculate it through a series of steps. Now we're at a very important point, and I would write this down if I were you. Lattice energy depends primarily on two factors. One, on the size or magnitude of the charges. So if we're looking at sodium chloride, the cation would be charged 1 and the anion would be charged 1. Okay? If we were looking at magnesium oxide, the charge would be 2 times 2. So that's what these are. Q's are charges on the cation and anion. So the lattice energy depends directly on the charges of the ion. The second factor that lattice energy depends on is distance between the ions once they're in the ionic compound. So R is the distance between the cation and anion. Okay? So as the distance between the cation and anion increases, so as they get farther apart, what happens to lattice energy? It goes down. So lattice energy and distance are inversely proportional. Lattice energy and charge are directly proportional. You don't need to know this constant. I won't ask you to calculate lattice energies, but I will ask you concept questions about what compound you might expect to have higher lattice energy and why. Let's look at a couple of examples. If I asked you to compare the lattice energy of sodium fluoride versus the lattice energy of calcium oxide, the very first thing you would look at are the charge on the ions. Remember now, the lattice energy is proportional to that weird infinity sign means proportional to the charge on ion 1 times the charge on ion 2 divided by the distance between the two ions. So the more important factor is the numerator, the charges. So the lattice energy for sodium fluoride would be proportional to 1 times 1. That's the charge on both of them. We can just put plus and minus. Divided by the distance. Okay. Normally you don't know what that distance is. Here I'm giving it to you. P is picometer. You don't need to know that. All right, so let's just look at the crystal lattice energy, how it would compare for calcium oxide. Well, the numerator, instead of being 1 times 1, would be 2 times 2, or 4, divided by the distance. So already the numerator for calcium oxide is 4, and the numerator for sodium fluoride is only 1. So as it turns out, the lattice energy for calcium hydroxide is much higher, perhaps by as much as a factor of 4, than the lattice energy for sodium fluoride. What does that mean in real life? It basically means that calcium oxide is a much stronger lattice. Okay, it has stronger attractions that hold it together. It's harder to break apart this ionic compound than it is sodium fluoride. Well, I goofed up on this slide. This is a first, I must say, that I wrote all the writing you see on this slide, I wrote without recording my voice, and now I can't erase it all because I messed up. Anyway, so it's very messy looking, but let me go ahead and try to give you the gist of it. What if I told you to compare the lattice energies of these 4 compounds? You would notice, hopefully pretty quickly, that the charges on all of them are the same. They all have, it's all +1 cation and all -1 anion. So they have the charges the same. So the numerator of the lattice energy formula would be the same for these. If that's the case, then you have to look at the distance between the ions. And the larger the distance, the lower the lattice energy, or the weaker the ionic compound is. So what is distance between the ions going to depend on? It depends on the size of the ion. Okay? The larger the ion, the larger the distance between the nuclei are. So think of it like people. If you have 2 very large people and they hug, their hearts are not going to get as close together as if you have 2 very small people and they hug. Their hearts will be able to get closer together. So the larger ion have larger D and smaller lattice energy. So cesium is the largest cation of this group because it's farther down. These are all in group 1A. All the cations are. And so the one at the bottom, which is cesium, is the largest. And cesium has the smallest lattice energy. Now I want you to ignore, they all have negative signs because lattice energy is an exothermic. So I want you to ignore the negative signs and not getting into that more now. I want you to look at the absolute value of these. So if you look at the absolute value, you can see that cesium has the smallest lattice energy and is the most weakly held together. So let's summarize what we've just learned about lattice energy. We know that it is dependent on the charges of the cation and the anion, and we know that it's also inversely dependent on the distance between the cation and anion. Look at charges first. So this first column shows lattice energies for cations and anions that both have +1 and -1 charges. And you can see that the lattice energy, these are presented in absolute value here. You can see that the lattice energy is decreasing, and that's because the ions are getting larger. So at the bottom here where there's weak lattice energy, there are larger ions. The second column have various charges. That's my dog snorting in the background. So if you assign charges, magnesium's +2, chlorine's -1. Don't multiply the charge on chlorine by, ignore the subscript. Okay, just put the charge on 1 chlorine. So the charge product is 2 for a magnesium chloride. Strontium +2, chlorine is -1, so that one's 2. Let's see, 2 times 2 is 4 for magnesium oxide, and that's the same for all of these. 2 times 2 is 4. Scandium nitride. Scandium is +3, nitride is -3, so those 2 charges multiplied together are 9. I'm doing absolute values again. All right, so as we would expect, this guy with the highest charges is going to have by far the largest lattice energy. It's going to be the hardest ionic compound to break up. You go ahead and give it a try yourself. Compare each of these pairs and tell which of the 2 in each case has a larger lattice energy. And again, I want you to think of absolute values. Forget the negative sign. Go ahead and turn the video off, see if you can figure it out, and then turn it back on and I'll tell you. The largest of these two is potassium chloride because potassium is larger than sodium. The largest, let's go to B, is sodium chloride because chlorine is larger than fluorine. The largest in C is magnesium chloride because magnesium has a +2 charge and sodium is only +1. And the largest for D is magnesium oxide because the numerator would be 4 for magnesium oxide, and for magnesium chloride it's only 1. So you're almost done with this lecture, but there's one last thing I need to explain, which is going to take about 4 slides. It's called the Born-Haber Cycle, and that is how scientists calculate lattice energy. I mentioned a few slides ago, very hard to measure directly the lattice energy. So scientists tend to use something called the Born-Haber Cycle, which is a series of addition of energies based on, similar to Hess's law. Hess's law just meant we added together enthalpies to get a net enthalpy. That's what the Born-Haber Cycle does. This slide is going to look somewhat overwhelming, but I'm going to walk you through, so it's okay. I will recommend at this point that you write down this formula. You will need it. This is a formula that I will give you on an exam, but for working your mastering chemistry problems or homework. So I'm going to correlate this formula to the diagram so that you can see what it's talking about. So it says the heat or formation of a salt. Salt is a nickname for ionic compound. So the heat of formation for any ionic compound, and that step is right here. Okay, and you should know what heat of formation is. It's the formation of 1 mole of any substance from its elements in their standard state. Okay, so that's heat of formation. So this energy difference is equal to all of these other steps that I'm going to describe added together. Some of them are endothermic, the ones that are pointing up going to higher energy are all endothermic processes. The ones with arrows pointing down are releasing energy and they're exothermic. So let me go step by step. So calculating, this is the Born-Haber cycle right here, and this is the formula used to calculate lattice energy. So what we're trying to get at the end of this is we're trying to calculate lattice energy by adding together all these other components. All right, so the first step is sublimation of the metal. What's the metal in this case? It's sodium. Okay, so the first step, notice, is taking sodium from its natural state of a solid to the gas phase. The second step is breaking the bond of the nonmetal. What is the nonmetal? It's chlorine. Since it's diatomic, you need to break that bond. So you can see here we went from Cl2 to Cl. We broke that. We went from here to here. The third step is ionization to make the cation. So that's taking sodium from its neutral metal to sodium ion. So all these steps I've talked about so far, endothermic, they all require energy to happen. So at this point we have the sodium cation and we have chlorine atom by itself, not diatomic. All right, the next step then is electron affinity. The definition of electron affinity is the energy involved in gaining an electron. So of course, to get to the ionic compound, this chlorine atom, which is neutral, has to gain an electron to become chloride anion. That is a energetically favorable process. It is exothermic. So now we're getting some of the energy back. The final step is the electrostatic attraction between the two ions, which are now formed. That's tremendously energetically favorable. It's exothermic, releases a lot of energy. So when you do this math, you would be given all of these values except for crystal lattice, and you would simply have to remember or know the formula, plug them all in, and you could then calculate the anticipated lattice energy of any ionic compound. Let's look at it for sodium chloride. So I hope you wrote that formula down, because here are all the values you need. Okay, so you need to be able to identify from looking at these equations what it's talking about. What is this one? This is sublimation of the metal. Second step is breaking the diatomic chlorine into individual chlorine atoms. Ionization energy, electron affinity, and lattice energy. So if you plug them all into the equation, what you should get for the lattice energy is minus 788 kilojoules. So make sure you understand that. Spend enough time on this slide so that you could repeat it yourself given these values. So here's a checkpoint as we end up this first lecture. Enthalpy of formation. Remember the definition. It is making 1 mole of whatever you're trying to make, which is magnesium oxide. So you got to make sure you get the formula right to begin with, right? Magnesium's +2, oxygen's -2. So they combine in a 1-to-1 ratio. So you have to make only 1 mole of it, and it's from its elements in their standard state. So magnesium is obviously one of the elements. All metals except for mercury are solids in their natural state. The other element is oxygen. It's a diatomic, and it's also a gas. So here is the equation for enthalpy of formation. Something you need to be able to do. Write an equation representing the ionization of magnesium. Well, magnesium, all elements start in their neutral state. They're not ions. And what does ionization mean? It means you've lost an electron. So magnesium, we know, has 2 valence electrons, so it's going to lose both of those valence electrons to give us the most common ion for magnesium, which is +2. And so that's how you would show the ionization energy for magnesium. Electron affinity means gaining an electron. So bromine, we're going to start from, even though bromine's diatomic, we're going to start with just the atom. Electron affinity means gaining. Bromine gains 1 electron to become bromide with a -1 charge, and that's how you would show electron affinity. That is it for the first lecture.